My name is Ines. I'm a planetary scientist at the European Space Station based in Madrid. And I am working personally on the icy moons of Jupiter, but you'll see that a lot of them are interesting. So first of all, let's take a look at the entire solar system. It's divided in two major groups. On the one hand, closer to the sun, there's the inner planets, or we call usually terrestrial planets because they're rocky planets like the Earth. So that's Mercury, Venus, Earth, and Mars. And after the asteroid belt, we have the outer planets, which are the gas giants. So much bigger than the inner planets and mostly made of gas rather than rock. So that's Jupiter, Saturn, Uranus, and Neptune. We are going to be looking at, each of this group is on one side of the what we call the snow line. And that's why we find the icy moons on that side, because the snow line is the limit after which the water ice could actually accumulate in planetary bodies and not evaporate as the solar system was forming, because it was far enough away from the sun. So if we take a look at the gas giants, all of them have a number of moons. I'll get back to that in a moment. But the three main icy moons of Jupiter are Europa, Ganymede, and Callisto. There's also Io that is not an icy moon, but that's one of the major moons of Jupiter that I'm not discussing today. Saturn has quite a lot too. But the main one is Titan. It is the largest of all the moons of Saturn. There's quite a few outside, beyond Saturn as well. But today I'm really going to focus on those five and really those four: Europa, Ganymede for Jupiter, and Enceladus and Titan for Saturn, because they're the icy moons that are really the most interesting to the community today. And I'm going to tell you why. So this is just a diagram of the interior of all those moons I told you about. And what they all have in common is that they all have a liquid water ocean underneath their icy crust. So when I say they're icy moons, it's because their surface that you can see here is covered with ice. Even Titan, this is the atmosphere. We're going to get to that in a minute, but they are all covered with ice. But underneath the ice, they all have a global ocean. And in the search for habitability in our solar system, so habitability is the potential of a planetary body to have life. That doesn't mean that these bodies have life. That just means that they have the conditions that we think are necessary for life. So this is a very important distinction. So the first thing we look for is liquid water. Usually we try to look for liquid water at the surface of a planet. The only one we know of in the solar system is Earth. But with the icy moons, we found another type of potentially habitable environment with liquid water underneath the surface. We also need two other elements to look for habitability, and that's energy. So in the case of the icy moons, this is mainly driven by tidal forces. So I don't know how familiar you are with that, but when you're at the ocean, the tide is what the tidal forces between the moon and Earth, for example, is what moves the ocean back and forth. So that's we have the same thing on Europa, Ganymede, Callisto, Titan, and Enceladus, but this is much more important because Jupiter and Saturn are so much bigger than Earth and the Moon are. So they create that stronger pull that this actually creates energy and thermic energy, and that's actually how these oceans can exist. The third element is what I like to call schnapps. So basically, that's the building blocks of organic molecules. So that's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So these three, if you can find these three elements in a planetary body, then they qualify as potentially habitable, and then you have to look for signs of life. So if we focus on Jupiter's icy moons for a minute, as I was saying in the beginning, they have those gas giants have a lot of different natural satellites. To this day, Jupiter has 79 that we know of, and we still discover more of them. Very recently, we discovered 10 of them in 2018. But the four main moons are the largest and the most massive. They are what we call the Galilean moons. So that's Io, Europa, Ganymede, and Callisto. And when I talk about the icy Galilean moons, that's just Europa, Ganymede, and Callisto, because Io is covered in volcanoes, not in ice. And those four satellites account for 99.997% of the entire mass of the 79 satellites. So they are by far the main planetary bodies in the system. So I said in the beginning that I was going to focus on Europa and Ganymede mainly because they are in the Jupiter system the main candidates for habitability. Europa in particular has, as I said, a water ocean, but its particularity is that the water ocean is in direct contact with the mantle. So that means that you can have a lot of exchanges between the water and the rocks, kind of like what you can have in the ocean floor for Earth. And that's where some of the life appeared on Earth. So that's very promising in the search for signs of life. You can wonder how we discovered that there was a water ocean underneath the crust of Europa. A lot of it is indirect measurements, but we also see signs of what we call cryovolcanism at the surface. So you're probably familiar with what we call volcanism. So on Earth, that's the volcanoes that you're familiar with. On Europa, there's no magma, but there's ice and water. So instead of magma and volcanoes, you have water and ice and cryovolcano. And you have two types of cryovolcanism. You have kind of more viscous type, creating that sort of features at the surface, what we call lenticulae and chaos. And you have very large bands at the surface of Europa, kind of like that can be compared to what we have again at the bottom of the ocean on Earth, and where the ocean floor gets renewed. So that's something that's again very encouraging in terms of activity.
Ines?
Yes.
Can I make a question of my own?
Of course.
The photo from Europa.
Yes.
These are cracks on the ice, or the ice is moving. Is it like the tectonic plates, something moving?
So this is a very good question, and this is actually a debate that we're having right now in the community. So a few years ago, a scientist from JPL shown that it could be plate, kind of like plate tectonics, but that would be driven by the ocean instead of magma and actual plates on Earth. They reconstructed some features by moving parts of the surface, and it appeared to fit quite well. But recently, the same scientists, when they pushed their theory and tried to understand how it could happen, they could not find a way to make it work with physics. According to them, it's not possible to have plate tectonics or something similar to plate tectonics on Europa.
Like glaciers.
Yeah, it's more like glaciers. It's more like glaciers. Those features, those chaos. But the mechanism of how they're created is still very much debate in the community, and we hope to learn more with the next missions. But it's still not a clear answer that I can give you. But
Okay,
the closest thing would be glaciers.
Thank you. One more, please.
Sorry?
One more.
Yeah, of course.
Okay. About the energy you talked about before, and the tidal moves. we on Earth experience the tidal movement of the sea. Okay,
Sorry.
the tides on Earth
Yes.
are made from the gravitational pull of the moon, of our moon.
Yeah. Yeah. Yes.
I wonder if we can compare them with Earth's tidal forces and Ganymedes or Europa tidal forces. How much stronger they are,
Yeah.
and what impact would
I,
they have?
I don't have a number in mind, to be honest. This is not my specialty, so I know that it's a lot more in the sense that the tidal forces on Earth are based on moon's pull on the Earth, but also Earth's pull on the moon. So I described it with the ocean, which is the thing that is most visible. But the truth is that even on Earth, tidal forces also create constraints on the rocks. So like there's a natural deformation of the Earth because of the tidal forces that we cannot always see. It is the same thing, but 1,000 times stronger
Stronger, yeah.
on the moons of Jupiter. And again, don't quote me on that. I don't have the actual number in mind. It's just
What?
a lot stronger. It's strong enough that it creates heating inside the moons that can sustain the ocean. So that's how strong it is. But
Okay.
I cannot tell you exactly how much.
Okay. Thank you very much.
Okay, so like I said, these are signs of a more viscous cryovolcanism, but uh, we are also exploring possible signs of explosive cryovolcanism with the possible plumes. Again, this is also something that's very much in debate. There's been a couple of observations with the Hubble Space Telescope that points to transient plumes on Europa, but we're having a hard time confirming those observations with other independent observations. So this is still something that we're trying to look at. If we move on to Ganymede, Ganymede also has a notion of salted water underneath the surface. Contrary to Europa, though, you can see here there's an additional layer of ice, high pressure ice, between the water and the mantle. So it's not as encouraging as it is for Europa, which has a direct link between the ocean and the mantle that is going to allow for a lot of exchanges. But some scientists have shown that even with this layer of ice, there can be some exchanges between the mantle and the ocean. So we really have to keep Ganymede in mind as well in the search for habitability. And fun fact about Ganymede, it is the largest satellite of the entire solar system. It's actually bigger than Mercury and very close to the size of Mars, which is saying something. But the most interesting fact about Ganymede is that it's the only satellite that has its own magnetic field. You might be familiar with Earth's magnetic field that creates the interaction of our magnetic field with the solar wind creates the aurora in the North and South Pole that you might have seen, like the Northern Lights, which gives amazing photos both from Earth and from the ISS. Well, Ganymede has the same thing, and it's the only satellite to have that. And even in the solar system, only Earth and Mercury still have a magnetic field to this day. So this is a very interesting feature. Let's move on now to Saturn's icy rings. If you have any questions on Jupiter's icy moons, you can ask them before we move on. Yes.
I have a question. How they're asking how the magnetic field is created on this moon. It's from the core that's spinning different speed from the mantle.
To be honest, we don't know. We still cannot explain why Ganymede has an internal dynamo and it's the only one. It could be something like that. It's probably something like that. That's the most sensible scenario that we have in mind. But again, we don't know. And we don't have a lot of data from the icy moons. So it's very hard. Everything I'm explaining to you now is from orbiters or from Earth's observation from Earth's telescope. We haven't landed anything on Ganymede. We haven't even orbited Ganymede yet. I'm going to tell you later about a mission that we're going to send there. So we don't know for sure, but it could be like on the Earth with the core that rotates, but we still have a lot of questions on the internal structure of Ganymede and of all those moons, really.
Okay.
I know it's frustrating. We really don't have.
May I ask a question? Sorry to interrupt. May I ask a question?
Of course.
So I researched a little bit about this online, and I found out that Jupiter's regular satellites can be counted. The big ones can be counted as dwarf planets if placed in around the sun.
Yeah, but they're not around. That's true in the sense that they are similar to Pluto, for example. That is a dwarf planet, but because they're orbiting Jupiter, they're not dwarf planets. They're natural satellites. But that's true that they are complex enough, and their evolution really puts them in the planet category. We study them as planets, really. It's just that because they're orbiting a giant planet, they are satellites. But technically, the moon could be too. Although it's not as evolved, I would say. But yeah, that's true. They're very, very complex planetary bodies. Okay. So if you don't have any questions for now, let's move on to Saturn's icy moons and not Saturn's. Sorry about that. So like I said, I'm going to focus mostly on Titan and Enceladus, but if we take a look for a minute, like we did for Jupiter, so I told you on Jupiter that the 4 Galilean satellites were, so that's what would qualify as dwarf planets if they were orbiting the sun, just those 4. They accounted for 99.997% of the entire mass of all the satellites. In the case of Saturn's, the major moon is really Titan. It accounts for more than 95% of the entire mass of all the satellites. Saturn has a lot of teeny tiny satellites, but 62 known so far. And so this is really, really small compared to all of them, but it's still the most interesting in terms of searching for habitability. And a very funny feature about Saturn's natural satellites is that, so you all know the image of Saturn with all the rings. Well, some moons are actually embedded in the rings, and because of that, they have accumulated material around their crater, creating what we call skirts of material. So there are moons with skirts, basically. And they have this very weird shape, and that's very unique to Saturn. If you take a look at Titan, so far on all the images I showed you, this is basically a yellow ball that you see, because Titan has a huge atmosphere. It is the only natural satellite in the entire solar system to have an atmosphere like that. But if we go in infrared, we can see the surface, and you can see how actually diverse it is. You have a lot of different geological feature at the surface, which I'm going to show you a zoom of in a second. So you always have to look beyond the atmosphere, and that this atmosphere is very a big complication in studying Titan. So this is back in the 90s and early 2000, we sent Cassini, which is a mission, a space mission to Saturn and its moons. And we also sent Huygens, that was a lander on Titan. And this is images of the descent. So before it crosses the atmosphere and as it got closer to the surface. And you can see that this is actually, you can actually see like mountains and dunes and lakes. And yeah, this is actually a zoom on a lake and on those dunes. A few interesting things. This atmosphere I told you about is actually denser than the one we have on Earth. So it's 1.45 atmosphere. So it's uh, like half more important as it is on Earth. And it is very comparable to what we can see on Earth, like those lakes and those dunes. But interestingly enough, this is not a lake of water like we would expect it on Earth. It is a lake of methane. So on Titan, there's a whole chemistry of methane and hydrocarbons. The same way there is a chemistry of water and oxygen on Earth. You must be familiar with the water cycle on Earth that creates the clouds, and then it rains and it creates lakes and other water sources. Well, it is the same thing on Titan, but just with methane. So when we look for potential habitats on Titan, we actually expect to find maybe forms of life that we would not expect to see on Earth that could be entirely methane based. So this requires a little bit of imagination, and we don't know what we'll find, but there's a whole field of methane chemistry that is really dedicated to trying to replicate what we could find in Titan. Let's move on now to Enceladus. As I said, it's a tiny moon of Saturn, but it's still one of the most interesting ones and the one with the most promise for habitability. It's really similar to Europa in terms of chemistry and internal composition and stuff like that. Contrary to Europa, though, where I told you that the active plumes were still in question because we cannot consistently find them. On Enceladus with Cassini, we found without question very active cryovolcanism at the South Pole. This is what we call the tiger stripes. So we can see plumes coming out of those stripes, and we think that this is directly related to the water ocean underneath. So technically, we could expect to sample the ocean through those plumes if we could fly through them. And just like Europa, the water ocean is in direct contact with the rocky core, with the rocky mantle. So this creates a lot of exchanges and the hope to find potential life forms in that ocean. Again, I really want to stress, we haven't found any type of life on any of those moons. I'm just talking about the potential and why we are interested in studying them further. And to that end, I'm going to talk a little bit about the exploration we've already done and the exploration we want to do of those moons. Except if you have a couple questions now before I get into that.
Ines?
Yes?
In Enceladus, we are expecting to find something like water, ocean water again.
Yeah, like, just like Europa, yeah.
And the cults like something like our geysers on Earth. The plumes you talked about. It's like geysers on Earth.
Yes, exactly. Yes, that's exactly true. That's exactly right. Yeah.
Okay.
That's what we've observed. I say plumes. It's really a question of semantics. It's the same thing. Yeah.
Okay. So we're expecting to find something like microbes.
Well, that's what we're hoping for, because of what I'm saying with the interaction between the mantle and the ocean. We think that this is a prime habitat for the for life to appear. So what we're hoping is if those plumes or geysers are actually related to the ocean as we think they are, we should be able to detect potential signs of life flying through them. But so far, we just found out those geysers in the last mission. So we would need another mission to try to sample them more consistently to see if we can find anything.
Okay. In Enceladus, I'm not sure. Methane based oceans are in Enceladus? No.
That's Titan.
In Titan. Thank you. Thank you.
Yes.
I was confused. And can their microbial life can be harvested with this whole environment of methane?
Yes. So far, again, we haven't found anything, but we haven't sampled really those lakes, but we have observed very complex organics from orbit. So we know that there's complex chemistry on Titan, and there's a lot of studies trying to replicate the conditions and potential analogs on Earth to see if we can find microbes, but based on methane chemistry. There's actually a mission that will explore Titan, its lakes, and its chemistry to see if we can find those. And I'm going to talk about it right after this.
It's a whole new chemistry for us, maybe.
Yes, exactly. And that's the thing that's really hard when we're trying to look for habitability and for life in general, is that we're really constrained from by our view of what life is and what habitability is based on our experience on Earth, because to this day that's still the only place in the universe where we know that life is.
Yes.
So it's very hard to even imagine other sorts of other possibilities of life. But yeah, it could be something we haven't even thought of yet.
Yeah.
That's what's really exciting. Okay, so if we take a look quickly at the exploration, those are all the missions that went through the system, not necessarily to the system, but also through the system on their way to their final destination. I already told you about Cassini and Huygens that were aimed at Saturn, its system, and Huygens on Titan. There was a similar mission to Jupiter and its moons that was called Galileo, and basically everything I told you so far is mostly based on those two great missions that allowed us to learn so much more about the moons. But like I also said, there's so much more that we need to understand. And to that end, we have two future missions, actually three that I forgot to mention here. But two missions to the Jupiter system. Oh yeah, so first I wanted to show you the evolution of what we know, but through what we can see through the different missions. So this is Pioneer 10. It's the first mission that went through the system. You can see the first images of Jupiter that we had are very, very blurry, but at the time that was revolutionary. This is the first images that we had for the Galilean moons. And this is now what we can do with the latest mission. This is from Juno, the current mission studying Jupiter, that has allowed us to learn a lot more about the clouds and the system of Jupiter itself. And this is what we can do with the Icy Moons. So I cannot overstate how far we've come since the first missions and what we know now. And this is the same thing with Saturn. This is an actual real picture that has been taken with Cassini in the last days of the mission. Of course, the rings were very clear from the beginning, but all the details we had to wait.
Ines?
Yes?
Sorry, I have a student in the chat asking, what about Voyager you just told us? She didn't understand that.
Voyager?
Yeah, I think that's what she's. Evangelia, you can talk yourself if you want.
Yes, of course.
Voyager. Please, your friends.
Hi.
Voyager. Is it in French?
I'm sorry, I cannot understand you. You're breaking up.
You maybe the mission, the Voyager that explores our entire solar system, and passes through
Yeah, so I told them
Saturn.
I started with Pioneer. So before Voyager, a lot of people know Voyager, but there was actually two missions before, two spacecraft before that
Pioneer.
were called
Yeah.
Pioneer. And those are the images I showed you. But I did select one image. Sorry?
Can you talk a little bit more about actual photos from Jupiter? From for this one. How the manipulation of the colors? How
So, yeah.
real it is?
So this is actually I cannot speak to it in details in the sense that I haven't done any of the processing on those. It's very counterintuitive, but the closest I think to reality, if I remember correctly, are the blue undertones, and that's not the same place on Jupiter. So the red spot is very much
the red spot.
But those two photos are quite close to what we would see if we were able to go to Jupiter.
So it's optical. We're talking about optical.
Yeah, it's optical. Yeah.
Okay.
Sorry, I should have said that. I assumed it was, all of the pictures that I'm showing you today, except the ones that I specified were infrared, are optical, are indivisible. Some of them, like the one of Cassini here, are so like the contrast is really is very strong. They really
the sun is behind now.
The sun
Saturn.
is behind.
Okay,
it's a lot of integration. It's a lot of it's a very long time of looking at Saturn, and they stretched, that was the word I was looking for, they stretched the colors, but it's still a real image with real colors. It's just that they manipulated.
It's very impressive.
Yes, exactly. But it's all optical in that case. And this is the same thing with Enceladus. So you talked about Voyager. This is actually the first image I could find of Enceladus was with Voyager 2. So maybe Pioneer didn't come close enough. But what I wanted to leave you on was really the missions that are going to go to the system very soon. So I myself, I'm working on JUICE, which is an ESA mission. JUICE for Jupiter Icy Moons Explorer. We're going to launch it next year with an arrival at Jupiter in 29, maybe 2030. It's a very long way to Jupiter. But the great thing about JUICE is that it's going to actually orbit Ganymede for 9 months. So we're going to be able to do more science than we've ever done on Ganymede and really try to understand everything we talked about with the magnetic field, the interaction with plasma and the magnetic field of Jupiter, the surface, if we can find places where there's activity and all that. But as a bigger objective, JUICE wants to really characterize the icy moons and the entire environment. So we're going to also have flybys of Europa and Callisto, maybe Io, but we'll be really focused on Ganymede.
Can they orbit around them?
No, we won't orbit.
The gravitational pull is too small to make an orbit around them, or it's another.
We could orbit Callisto because we're orbiting Ganymede and it's closer, but it is very hard because of the gravity pull. It is very hard to make any types of movements in the Jupiter system. It's a very complex system, and people have been working on it for years to get the trajectory right. We're going to try to use the different flybys to actually help us get closer to Ganymede. Because I haven't talked about this at all, but I said it is going to take us 8 years to get to Jupiter because we're going to use gravity assist from different planets. And that's what we're going to do in the Jupiter system. We're going to use the flyby of Callisto, of Jupiter, of Io, and Europa to decelerate into the system and for it to be easier. Europa is a special case because it is very close to Jupiter. So that means it's that much harder to decelerate to Europa's orbit. But also, we have what we call planetary protection. So I talked a lot about the potential for life, the very high potential for life of Europa and Enceladus. And for that, they're very protected in the way we can, and very restricted in the way we can send mission to them. You cannot get too close to Europa, because if you crash into it, you would risk contaminating it.
Contamination, yeah.
Yes. So for those two reasons, it's very, very tricky to be in orbit around Europa. The other mission that I'm going to tell you about, and it's dedicated to Europa, even this one, so that's Europa Clipper from NASA, is not going to orbit Europa. It's going to orbit Jupiter and fly by and make a lot of flybys around Europa because it's a lot easier. There's also the question of radiation at Jupiter. There's a lot of radiation in the system. So any mission to Jupiter is very challenging. This NASA mission is going to be launched in 2023 and arrive at Jupiter probably in 2028, but it's not, it depends on the launcher. There's not been a definitive decision on the launcher. Its objectives is really very Europa-centric. They want to study the real potential of Europa to harbor life. They also want to potentially select landing site for future missions. There's one mission called Europa Lander. For now, it's just a project, but it's getting traction and it's gaining funding. So maybe in a few years, we'll see a lander on Europa. And Clipper really is aimed at mapping everything and really trying to find the best possible sites for such a mission. The one mission I forgot to mention here about Titan, and I think about it because of your question about the methane lakes, is a mission from NASA called Dragonfly. It's gonna be launched in 2026, arrive at Titan 2034, and it's gonna be a helicopter that we're gonna drop into Titan, and the helicopter will be able to analyze quite a few different features like lakes, like dunes, in the hope of finding complex organics and potential traces of life present or past. So that's a very exciting mission that got selected last year. And that's it for me. So the few messages I want to leave you with is the three main candidates for habitability are really Titan, Enceladus, for Saturn, and Europa. But also, I wouldn't discount Ganymede, even though a lot less people live in it. But we have still a lot to learn, and we have a lot of exciting missions coming up. And I think you're all in high school now or close to that. So you could be working actually on those missions. Like I said, it's going to take us a long time to get there. JUICE is going to arrive 2030. Clipper is going to arrive 2028. And Dragonfly is going to arrive 2034. So you could absolutely be working on those missions if you're interested in planetary science. That's it for me. Thank you for listening. And I don't know how much time we have left, but I'll take your questions if you have them.